Good morning. So we're already halfway through. So that's the previous 4 sessions. In each session, I put one of slides at the end of your handout, so-called intended learning outcomes. So basically, you need to spend like a couple of minutes to review after each session, just see what you what I try to introduce in each session. So I just copy that individual slides here together, put it together. So in the first lecture, I just try to review the general acquisition. So some of you guys actually learned this from previous lectures, but some maybe not. So I just try to give you the general overview. So the basics, in the first lecture, we try to understand those concepts. First of all, the basics of seismic method. In fact, if we just say one word for the basics of seismic method, I think one key word will be superposition. That's the key, right? Superposition. Mathematically, it is called convolution. That's the key. And we also showed you some seismic short-getters. So you can, based on the behavior of coherent events on the seismic data, you can recognize different types of waves, like first arrival reflections or some coherent noise, so on and so forth, right? That's the basic thing. In the first lecture, we also introduce something called the Z transform. Try to, for convenience, actually, to introduce the discrete Fourier transform, right? So Z transform is a polynomial. Each individual term in the polynomial is composed of coefficient and the Z power, right? The coefficient is the actual sample value, and the Z power, the power actually is the index of the time sample, right? Okay, so the Z transform. And then you replace the Z operator by E I omega delta T. That's easy transform to the discrete Fourier transform, okay? So the discrete Fourier transform is not simply a discrete form of a continuous Fourier transform, right? You learned from high school, from year 1, year 2 of a undergraduate study here. You learn the continuous integral format of integral form of Fourier transform, right? But here, I just tell you that Z transform is the tool for everybody to get the concept, discrete Fourier transform, okay? Why we do the discrete Fourier transform? Because in the discrete Fourier transform, the operator will be periodic of 2 pi. Because 2 pi, we can eventually introduce lead to the so-called fast Fourier transform. So in the seismic analysis, seismic process, seismic image, almost every step will employ that technology called a fast Fourier transform, FFT, right? And the calculation only end up only 2 terms. You just do the 2-term complex calculation and sum them together. That's get Fourier transform. It's very, very fast, typically for long time series. Also, because of introduction of Z transform, introduction of DFT, you can implement the convolution in the Z transform domain or equivalently in the Fourier transform domain very fast, right? Convolution in the Z transform domain or in the DFT domain becomes multiplication of 2 complex values. That's easy, isn't it? two complex values. How to do the modification of two complex values? It's easy. Just say amplitude multiply each other, and the phase just added them together, right? Okay. The correlation similar to convolution. Also, this is also a product in the Z-transform domain or DFT. They're also a product or a modification of two complex values, but one is the original complex value, but another one is a complex conjugate complex value. Okay. So explicitly will be amplitude. Two amplitudes will be multiplied each other, but two phases will be subtracted, right? That's the only difference. You can see by employ Z-transform concept or DFT concept, you can see convolution and the correlation. It becomes so easy in terms of calculation, right? And this is why modern days, when you do the data processing and the imaging, everything becomes so fast, right? I also demonstrate some examples of land seismic acquisition and the marine seismic acquisition, right? Typically, we should know for the land seismic acquisition, because the receivers is on the surface of Earth, right? We cannot record the pressure. We only can record. What we only can record is the particle velocity, right? So then on land acquisition, what the wave field we record is a particle velocity. So you have a vertical components, horizontal components, right? Actually, 3D components will be a completed representation of the waves, right? You have a vertical and horizontally, you have two components. One is parallel to the line, another one is perpendicular to the line. If it's not, you just do the mathematical rotation to get 3 components, right? So that's the for land. For marine, because the receivers are put into the water, right? Shear modulus of a fluid is 0. So that means there's no particle velocity. What you can record is only the pressure, right? So the water have a pressure. What we can record is just record the pressure, okay? For both of, in the marine, we call the hydrophone, because in the water, right? On the land seismic, we call the geophone. But both in the field, what we record actually is either pressure or particle velocity. They are converted to the voltage, right? Current voltage. So actually what we record is the voltage, right? So that means amplitude of seismic data is always a relative component, okay? So that's the key difference. For the source, for land seismic, we actually revealed there are 2 types sources routinely used in the industry. One's dynamite, right? But gradually become difficult for using dynamite as a source. A, environmental issue. B, security issue, right? You cannot easily transport your tons of dynamite from different countries, right? Gradually we use big truck, which is called warp size, right? The signature of warp size is different from any other sources, including the dynamite, including the in the marine environment. We use air gun. Right? They have try to mimic the impulse source. You have a very short time period, very short time duration of signature. But for warp size, actually the source signature is very long. If we say you recorded seismic data for like 6 seconds, your source actually maybe 3 that size, right? Maybe 18 seconds, even longer, okay? And this variable size signature actually is called sweep, which means you have a harmonic signals, but the frequency of harmonic function varies along the time, right? And the different sweep types, people can use. You can have frequency from low to high linear increase, from lower frequency to high frequency, or from lower frequency to high frequency decrease, or nonlinear. Okay, but any nonlinear signature can be decomposed into a group of a linear signature. Right, this is one of a mathematician called Costa. So eventually, the correlation between the source signature and the recorder signal, which is the wavelet we called Costa wavelet. Okay, so basically, the mathematical concept is that any nonlinear sweep can be decomposed into a series of linear sweep. So this is a principle. For marine, we use air gun. You just have a pressure on the water in the water. But the one thing in the marine environment is very, very significant influence to the signature, to the wavelet, is called surface ghosting effect. Surface ghosting including the source side, because the source is not on the surface, right? At least like 8 meter or 6 meter in the water. And the receiver side as well. Receiver side maybe another 8 meter, right? So we did learn that for use a Z transform to represent the ghost, because we have one original signal, another one is bouncing back from the surface, which is called a ghost. So these two samples we call a dipole filter. Dipole filter means you have two samples, right? And we use a Z transform as a tool to find out the ideal bandwidth of your signature. So that's actually determine your acquisition parameters. Okay, so this is the everything almost we learned from lecture 1. I just use this diagram. On the left here, this panel here, I have a layered model, and attached with there are number of interfaces, and for each interface we have called a reflection coefficient. Right? Reflection coefficient actually measures the property difference between the neighboring layers. Okay, so as I said, you have a signal. This is the reflectivity. Here we present it like in this way. Ideally, each of the reflection coefficient should be a spark. If you have ideas such as a geological model in depth, but in the data domain, as in time, right? As I emphasize, we should distinguish something from it's a model space or data space, right? Here, the first panel here, that's definitely model space, right? Because it's in depth, which is geological model. But the second one here, although we present it as a spark here, but that's in the depth, in the time. So it's in data, in the model, in the data domain. Okay, so that you cannot confuse them. So you have this sparks. Actually, the seismic data is composed of, seismic series is composed of by a convolution. So this reflective series convolve with the signature. You end up, each of this convolve with have this reflection coefficient, reflection together, right? And the superposition means you just sum them together, you end up to the right-hand side. That's called superposition. Okay. So this signature is here. We call it wavelets. It's a composed. It's a composed of the source signature, composed of filtering effect of the Earth, right? Such as attenuation, such as velocity dispersion. Also includes instrument effect or receiver effect, right? Like, for example, the receive side ghosts. So all this are included. So that's called a wavelet. Wavelet is not equivalent to the source signature. Okay, wavelet is the actual combination of all these factors. Okay, so mathematically, this is a convolution. Superposition, just straightforward superposition. Just sum up each individual wavelet together. Just called superposition, which means stacking, right? But mathematically, it's called a convolution. Okay. The processing here, what we try to do is, because we know a seismic trace look like this. The one for a straightforward target is try to from here to recover this, because this one can be easily used for geological interpretation, right? Because you have a, you know exactly where the interface is, and then because of the reflection coefficient here, you know the difference in terms of physical properties, right? And then we can know the geological property and the geophysical property of the subsurface media. You see that? So this from here to here we call it convolution. That's forward calculation. But data processing is inverse processing. So based on data, you try to do this. Okay. But why this course is called advanced seismology? Because you can see here, this data series. Here we have two unknown variables. We don't know the reflectivity. Also, we don't know the wavelet. Right? This, you think about it, you have one equation, but have two unknown variables. You see that? Okay. So that's for solve this problem. That involves a lot of assumptions, right? And a lot of the constraints. Okay. One of two of fundamental assumptions are linearity and the time invariant, right? Time invariance. So there's two fundamental assumptions involved. We will see detail. So that's the first chapter. Oh yeah, okay. And in the first chapter, when we introduced that transform, so maybe this is the one with formulas you need a mathematical formula you need to remember for this course. Actually, one of them, right? It's easy, isn't it? You have a time series A, time series B. For example, in the previous slides, that's the refractive series. This is a wavelet. After transform to the Z transform refractivity series called AZ. Wavelet transform to BZ. If you multiply them together, you end up to convolution result, but in the Z transform, right? And use this formula, you can easily derive this mathematical convolution formula. Okay, that's the easy way to do that. For chapter 2, there's another mathematical formula. I think it's quite easy to remember. It's this one, the sampling theory. Another terminology called Nyquist frequency or Nyquist sampling rate. Nyquist, right? Henry Nyquist. But what it really means, it means for the maximum frequency for the digitized time series, the maximum frequency you can have without any distortion. So distortion means if any frequency higher than the maximum frequency, there will be folding to the wrong place. What they call it aliasing, right? When I introduce the concept to you, I give you the example, like a 007 driving car, right? When they drive very fast, you can see the wheels actually going back where it was, not forward, right? Because your eye sampling is digitized and your sampling rate is too large. Okay, so that's the example. Okay, and this chapter 2, we also learned a very, very important concept called CMP. This actually throughout this whole lecture. The CMP concept is not only for the data processing, but in the field acquisition, you also consider basically CMP is a linkage between the acquisition and processing, right? After that, we're also talking about some pre-processing, typically in the field before you pass data sets to the processing house, right? Pre-processing includes amateur correction or amateur recovery, right? Because the acquisition system, we have a limited so-called dynamic range. You have a maximum and the minimum values you can record. It's just called a dynamic range. Depends on how many bits of a recording system, right? If we anything more than that, you need some in the field. You need to do a gain control. All right. So first thing you want to do the gain recovery. That's one thing. Secondly, because of so-called spherical divergence, your deeper part of the refraction seems very small. You cannot see that on the row together. You do need to do something called AGC, automatic gain control. Just boost the later part. Just see in this acquisition whether we actually acquired the reflection from the deep part, deep reflection. Okay. Sometimes, typically for lens size, you need to do some filtering, get ready for like a ground roll, just see whether the weak reflections actually acquired from the field or not. Otherwise, you need to redo that, right? And well, this also leads to like a noise removal. So this is the one equation I think we need to, if we want to remember any equation, this is the one over 2 delta. That's easy. Okay. So that means if your sampling rate is fixed, the maximum frequency without the distortion you can present in your data is this one. Right, so 1 over 2 delta t. Okay, so that means within the maximum frequency that can sample without distortion, right? This is the fundamental consideration for both acquisition and processing. If you haven't, if the delta t too big, and this one is relatively small because delta t big, this one relatively. So any frequency higher than this, if you haven't recorded in the field, that means you have no chance forever, no chance to recover that. So you must in the field try to use the smallest possible delta t to get the maximum frequency without distortion. That's the one formula. Based on the frequency domain spectrum, we introduce something called filtering. Filtering usually, when we say filtering, really means most likely we use a series of weighting coefficients to multiply your frequency spectrum of the seismic traces. Okay? So your seismic data transformed to the frequency domain. Your seismic data becomes horizontally frequency, vertically the amplitude, right? And that this will be the weighting coefficient multiplied to the individual frequency. Right? That's in the time domain. In the frequency domain, it's a multiplication. Something we call the filtering. Equivalently, if we convolve this multiplication in the frequency domain to the time domain, it is called convolution, right? So filtering, convolution are the same concept, but just in a different domain, right? One in the frequency domain, one in the time domain, okay? So generally like a low passing filter, so that means here you just simply use a weighting coefficient 1, just multiplies. You do not change anything, but here it's just 0. And here's 1 outside of 0. This is called a band pass. And this is called band rejection. One of our filters is called notch filter. Notch filter is a special case of band rejection. Notch filter typically, if we want to get rid of the industrial frequency, industrial electric frequency, right? Different countries may have a different frequency for the electricity, 50 hertz or 60 hertz. So you have a notch here. Okay, that's one thing. So filter seems easy. Either 1 or 0, you multiply that just coefficient to your frequency amplitude. But important thing is here, you cannot have a sharp boundary here. You must have a so-called tapering here to try to minimize so-called Gibbs phenomena. Gibbs phenomena, right? The Gibbs phenomena means you have some part of frequency amplified, amplitude, some actually suppressed, right? So you do need a certain slope here. So it's called tapering. Okay, that's the practical thing. So when you design filter to process data, make sure you always apply this. Okay. That was lecture 2. For lecture 3, we already said set transfer domain, how to do the convolution and the conversion. Okay. And the difference mainly in this chapter 3 is called the inverse filter. Inverse filter is also a filter, but the inverse filter is designed by 1 over the original filter. Right? So this is the way. To understand the physical meaning is if you think your data is the result of a filtering, so some like Earth filtering effects on your data, like a ghostly, ghost, receiver ghost or source ghost, there are filtering effects to your data, right? So now you try to remove this effect. You try to apply 1 over that filter to that. So that's the easy way to try to remove, try to recover something. That's called inverse filter. In order to have a reliable or stable implementation of inverse filter, there's one condition for the filter. What is? Do you remember? What's the condition for the filter? That's right, absolutely right. The filter must be a minimum phased. Must be minimum phased, okay? So minimum phased is the condition for the filter. Otherwise, you cannot create a so-called causal stable filter, right? Causal means you have non-zero elements before time 0, right? Issues with the filter application, I summarize here 4 issues. Okay, first one I talk about FFT. Do you know what's the issues related to filter application? Why I mention FFT here? Anybody remember? I already said in few minutes ago, FFT is a fast calculation, right? Because you can easily fold your time series by every, half folded, another half, right? So that means the length of an input time series should be power of 2. If it's not, what we do? That's right, called 0 padding. We need to make at least for the power of 2. Okay, so 0 padding. If not 0 padding, or if exactly the same, or the data series given to you is exactly 1 over 4, for example, you do not do 0 padding. What happened? Is the second one here called wrap around, right? Because FFT employs a property of a periodic signal, right? So you always assume your input time series is repeated many times. Okay, that's the implicit assumption in your FFT. So that means you assume your data is repeated. If we do not have enough padding, the end of time series will be sort of overlapped by the beginning of the next period, right? So the two periods of signals actually overlapped, all right? That's called wraparound. Okay, so the padding not only for FFT, but if you have a 2-time series repeater, but they have a gap in between, right? You can easily separate them. They have no signal overlap, just wrap around. Gibbs phenomenon, we just mentioned, when you do the filtering, you should have a slope, have a tapering effect. Otherwise, have a Gibbs phenomenon. Okay, anyone can tell me what the concept of pre-whitening here means? Right. The purpose is to try, mathematical purpose is to try to avoid 1/0, right? Division to 0, or not in the mathematical, in the computing age, it's not necessarily 0, because in your computer, 0 will never be 0, right? So any small numbers, if 1 small number, that means you enlarge it. So basically easy to boost the noise, okay? So you do need that's called stabilization. So this concept actually have at least 4 of explanation from different angle. First of all, I said it's stabilization, because you try to 1 something very small towards 0. Not necessarily 0, right? But anything small. So you add in a positive energy on that. That's you will have avoid the 0. Okay. So if actually the filter is 0, 1/0 plus something, that becomes 0. Yeah. Or becomes, it's not 0. So this the pre-whitening, the one concept. Second concept, what I call pre-whitening is, if you remember, we're talking about a Wiener field. Wiener field, we try to, Wiener field is a matrix A multiplied by a filter and then cross correlation, right? So the matrix A is autocorrelation. Autocorrelation. Pre-whitening concept is from here. It's from autocorrelation for noise. So if we assume something with data that says do have noise, so you give a quantitative measurement. So you add in noise to the Venn diagonal. The third one, we're talking about least square actually. That's the least square means you have a in the least square problem, you have a data fitting. Basically, you try to do the deconvolution, you have a ideal data set, but you have a real data set, right? That if we fit them, they always have a misfit. Just one thing called data fitting part. But also you have a model constraint. So I expect my solution will be very close to some solution, right? So in your inverse problem, you have a data fitting and a model constraint. So how you balance them? What's the trade-off? So this parameter actually trade-off parameter, right? That's the 3. The number 4 actually, I just you don't have learn that. Number 4 basically is called a covariance. Okay, so that actually this parameter is a ratio of data covariance, signal covariance, and the noise covariance, right? But anyway, at least you know they are not only mathematically stable, useful, but also have a physical meaning behind it. Meanwhile, also have a mathematical necessity here for this pre-whitening. Okay, so now we already said least square. So how we generate least squared, least squares inverse filtering? We use autocorrelation, generate a matrix, and the cross correlation generate a vector, and we use Lorentzian-Recursion method to calculate filter, and then apply filter to your data, right? That's the least square. Based on this method, we practically for data processing, we introduce a 2 deconvolution. Deconvolution basically is inverse convolution, okay? Convolution is a filter applied to to your data. You know something there. But now you try to get a filter and do the inverse filter, do the so-called deconvolution. One's called spark decon, one's predictive decon. All right, let me show this. Okay, first of all, we said if we want the inverse filter, we need the filter be minimum phased. So how we do the minimum phase? How would we check whether it's minimum phase or not? So we can decompose a time series into so-called dipoles, a series dipoles. But for each individual dipole, you need to find A and B. You need to make sure absolute value A greater than absolute value B. That's the condition, right? Each of those, okay? Why? Because in this formula here, if I put the one over A in the front here, you have a 1 plus something, right? You learn the Taylor expansion. Zeta here is a time unit operator. The magnitude of zeta is 1, right? Because E I omega delta t. So cosine plus I sine, right? Cosine square plus sine square always equal to 1. So the absolute value or the mode of zeta is 1, modulus, right? But B minus A, either positive or negative here, doesn't matter. That ratio, absolute value should be less than 1. Otherwise, otherwise Taylor expansion will not converge, right? That's what we learned from your, I don't know, maybe high school or year 1 here, right? So you can see that if we just A absolute value of A greater than absolute value of B, this time series is converged, guaranteed to converge. That means we can trunk cut at any order, right? So that means your inverse operator, inverse filter can work, okay? That's right. The spark deconvolution, as I said, the least square inverse filter is generated by autocorrelation and the cross correlation, right? So in the autocorrelation, if we have a seismic trace, if we do the autocorrelation, you have a 0 lag here, and you might have you can see the multiples. That's, for example, in the water environment, air gun. That's first order, second order multiple. That's not seismic trace, okay? This is autocorrelation of seismic trace. Autocorrelation means the seismic trace correlates to itself, yeah? So the spark decon really means you try to reshape this signature into a very nearly spark, right? Spark wavelet will have a high resolution when you do the layer interpolation. So that's highest resolution, okay? And the one parameter here is the operator length, so basically filter length, okay? So it means how many samples in the vector F when you do the AF equal to B calculation. If this length is very short, that means only reshape this one, but those refractions are untouched, right? Keep it unchanged. But if for longer one, you can see this also removed, okay? Because you can see this, we can remove the multiples. It leads to another concept called a gap deconvolution or predictive decon. So if the signal is predictable, which means you have this, and then you can predict this, you can see this time period is constant of only the priority, negative, positive, right? So you can easily predict this. That's called predictable. Because predictable, you can get to level this by predictive decon, right? But why we call the gap decon means at the beginning, this part, we try to keep this part untouched, right? Maybe you do this spark decon already, and then you do this, okay? Sorry. So in fact, in the software, in that processing, or in mathematical term, predictive decay and gap and spark decay, they actually same software, same implementation. Only difference is in the spark decay, your predictive lag is one sample. But this predictive lag means within this time range, signals will be untouched, right? Okay. But just field length, just see how long you take it. So in your profile, you will see when you display your subsequent profile on top, you usually display the autocorrelation at the bottom, so you can see before and after deconvolution. That was chapter 3. Chapter 4, what we did, we're talking about the CMP concept in the processing term. And for each individual CMP gather, we work out how many traces in that gather. The number of traces we call the fold. Okay? On the CMP display, CMP gather, we can see the refraction appears to be hyperbolic curve, which means the travel time depends on the offset, right? And the dependency is that hyperbolic equations, t squared equal to t naught squared plus another term. That's term called NMO correction term, right? We use this CMP gather and use this hyperbolic curve. We do velocity analysis. What we do, we try to use different velocity to do the NMO correction, see whether we can maximally make the reflection be flattened. That's the, right? So if it's flattened, that velocity will be the best velocity for NMO, right? Okay. In the short offset assumption, the NM velocity can be considered as RMS velocity. But NM velocity is from data processing. RMS velocity is from a mathematical term, right? Mathematical term. So based on RMS velocity, we can derive the interval velocity. This formula called the Dix equation. Okay, Dix equation. And then what NMO for? NMO question for NMO have the functionality. If we stack them after NMO, NMO really means for each individual trace which has a non-zero offset, right? What we do, we shift every samples along this trace and make it back to so the time becomes the time at the zero offset, and then you sum them together, right? When you sum them together, signals will be enhanced because they correlate without any time shift, right? However, the random noise will be somehow suppressed. Do you know the famous formula actually given by Einstein? If you have n traces within a CMP gather, after stacking, what's the ratio of random noise? That's right. The random noise will be reduced by square root of n. Right. So that's why we need the redundant information, right? So for individual data sample, if we have 100 traces, stack them together, your noise will reduce by 1/10, right? If you have 1,000 together, 1,000 is difficult, isn't it? But if you have 10,000, you have 100 times lower. So it's absolutely depends on number of traces. So 1/1. That's for random noise. Okay. Also, stacking have a positive effect on multiple attenuation. When you use correct velocity to get the primary flattened, the multiples actually undercorrected. So multiples still have a move out. So if we sum them together, because the coherent multiples, they have phase out phase, right? So you sum them together, they will somehow cancel each other, right? But for the near offset, the time difference are very small. So that means and still have residual. Okay. One tool we use, we just do the called inner muting. We remove the near offset part. So finally, we have a stacked system profile. So what we said, after the first 4 lectures, which we actually achieved half of the objectives. Well, this is the concept. If we want to remember, you really like a mathematics, if you like. This formula simply say from this source point to the receive point, what the travel time is. Right? You know exactly the distance, which is 2h, and you know the velocity, because here you do the average velocity, right? You know the velocity is also 2h divided by velocity. This is the travel distance, travel time from here to here. But you also know at the zero offset the travel time from here down here go back. That's the T naught. And then you have this formula. Squared equal to squared plus squared. That's called a hyperbolic equation, right? So what we try to do again, really means you try to work out the best part of this to make all these traces become T naught. That's it. That's the only purpose. So that's the review of previous 4 chapters. And of course, at the end of whole lecture, day 9, we'll have a whole review for the whole course. There's not many mathematical formulas, but unfortunately, because we have a sort of dual mode here, I cannot write on the board, you know, but otherwise we just have a very simple derivation or simple calculation on the board will be much easier. But we do not have, so far we don't have many equations to remember, right? I think for you guys, what you try to do is every step here, you try to understand the physics behind any simple form, mathematical formula or complicated mathematical formula. Do not worry about the mathematical formulas detail, but you need to understand the physics meaning behind it. That's important. So we said stacking can help us to reduce part of our multiples, but not completely, right? So today we try to do something called multi-channel filter. This is a session, I divided this session into 4 parts. One is called the FK transform. We learned the F transform, which is called Fourier transform. F here stands for the frequency, but we also now today try to do, we call the 2D transform, 2-dimensional transform. Another dimension is spatial, right? Temporal and spatial, time and X, okay? Of course, because we have a spatial, so we have an Edison issue in the 2D domain, in a 2-dimensional way. We learned that Edison in 1-dimensional, you know, high frequency, which higher than the next frequency will be forward to the wrong place in your frequency access, right? Now we have a 2-dimensional field, a 2-dimensional spectrum. We'll see the Edison issue. Okay. Understand the FK transform under the Edison issue, then we can design FK filter and see how it works. And finally, I'll give you an example for multiple attenuation. As we said in previous section, stacking is good for remove part of multiples, but not completely, right? So we just try to see this one, right? FK transform. Let me just repeat what we learned for the Fourier series. what we learned about Fourier series. Fourier series provides information on repeatable nature of signal. Right? As we said, we also repeatable because we use sine or cosine harmonic function to correlate to your original data. So Fourier transform is correlation. Use a constant frequency harmonic function to correlate to your data. And the correlation coefficient is the amplitude spectrum. And because you use cosine and sine together, so the lag between sine correlation and the cosine correlation, you have two correlations, right? The difference between the two, the lag between the two, called the phase, right? Understand this part now? Okay. The physical meaning of Fourier transform fundamentally is a correlation, but we use a cosine, which is harmonic function, cosine function, and the sine function. We use the two functions to correlate your original signal, whatever signal, okay? So the correlation coefficient, you have cosine part, sine part, so you have a square root of that. That's the amplitude. You have a cosine correlation coefficient, sine correlation coefficient, but the lag, the difference between this, basically ratio, is the phase, okay? That's easy. So that means we assume your signal is periodic. It means because cosine or sine function is from negative infinity to positive infinity, right? We do not say we only correlate this part, right? That's why we assume your original signal also periodic. Okay. Why we do that? Why we can do that? Because we assume here called linearity and the time invariance. Okay. But seismic data, in fact, this very, very fundamental assumption. This is why every time, if I have chance, I will repeat. Those are the two fundamental assumptions. Those fundamental assumptions are quite useful for data processing. Okay? But when you use seismic data for the geological interpretation, for geophysical characterization, you cannot no longer, assume these two assumptions. You must consider their data is not linear and it's not time invariant. Fourier transforms used for convolution. The usefulness was very simple. You just transfer very sophisticated convolution in the time domain to a modification in the frequency domain. That's very straightforward, very easy. Depends, you already transfer your data series, use FFT, fast Fourier transform. Fast Fourier transform so fast, you almost ignore the time of a calculation, and then you just do modification, and then you do inverse back. So same thing. And the Fourier transform can separate somehow signal and noise, because signal and the noise, they occupy a different frequency range, different frequency. For example, ground law have extremely lower frequency, so you can use a lower cut filter to remove that, right? Or notch field, we can use notch field to get rid of industrial electricity frequency, right? So this is the way. Very useful generally for filtering. So most likely you design filter, and you most likely transfer your data and the filter into frequency domain, and implement the filtering in the frequency domain. Deconvolution is also a filter, which is inverse filter. You also implement deconvolution in the frequency domain. So Fourier transform is a very fundamental tool for seismic data analysis and the imaging. The concept I said, for a signal look like this, very simple signal, you have a different frequency, horizontal frequency, different frequency harmonic function. That's from negative 0.5 to 0.5. This is 1 second, which means how many circles per second means the hertz, right? The frequency. So in the first one here, you can see from here to here, peak, and to the negative here, that's the frequency is 1. You see that? And the next one, you have a half the peak here, trough here, peak here, trough here, peak again. So basically 2 period. Is it 2? So use a harmonic function, which, right, sine or cosine function. Here, this cosine function, right, because we're talking about real part. This function, to correlate to that, you get a result. And the cosine function, this cosine and sine function do the same thing, right? Okay. That's the one decomposition. That's the Fourier series. If we sum them together, you come back to the original signal. Talking about phase shift, if we just that diagram in the previous slides, you sum all the together because all the peaks enhanced. Apart from the central part, gradually here completely cancelled, but here gradually decayed. You can see this have a 0 phase, right? Now, if each of this have a 90 degree phase rotation. Phase rotation means here the peak is here, 90 degree. Let's say cosine something. Now this becomes a cosine something plus 90 degree, right? Here cosine 0 is 1, right? But no cosine 90 is 0. See that? And the cosine negative 90 degree was here, 0. But now negative 90 plus 90 becomes cosine 0. So here's 1. You can see that have 90 degree phase shift. So 90 degree phase shift, if you sum them together, you end up look like this. So from a symmetrical, the waves, the signal, it was in the symmetrical form, right? But now it becomes asymmetrical, right? 90 degree have a positive peak, negative trough, almost identical, but just in an asymmetrical way. See that? Right. The same principle applied that will apply to the time series now can apply to another axis. If we have a matrix of data, you have not only horizontal axis but a vertical axis, right? So you can do the same thing to the spatial. So so-called time series analysis, the time is not necessarily time, not necessarily be the physical time. Basically, it's a sampled series. We call it time series. So that sampled can be not only in the time sampling, but also in space sampling. In seismic data, when we talk about CMB data, we have not only vertical axis time, but the horizontal axis is the distance, right? Offset. So basically, you think about the continued variation around the spatial direction, but in individual traces here, actually, individual trace is a sampled signal. You see that? So you can use a Fourier transform also around space direction. Okay. So in Fourier transform around space direction, we usually call it K transform. K means wave number, which means called a spatial frequency. Frequency in the space direction, right? F is a frequency. We simply call frequency. Actually, it's temporal frequency. It's frequency with respect to time. K here is frequency with respect to space, right? So you have two frequencies. One is called temporal frequency. One is called a spatial frequency. Okay. So for the K transform, basically use a sine or cosine function, but the cosine or sine function is a spatial function. The variable is no longer t, but it's x. Okay. Right here, this bit of trick here, I need to spend a little bit here. When we do the time domain, time series to the frequency domain, if we are seismic traces in real valued, after Fourier transform, you only have positive frequency. You do not have negative frequency, okay? So from if your time series is in real, it's real value, right? After Fourier transform, of course, your frequency components is complex valued. You have amplitude and the phase is complex valued, but you only have non-negative frequency, let's say that way. Why? Because the complex conjugates, okay? However, after you do the first Fourier transform, you're already in the complex domain. And then you do the second Fourier transform. So complex Fourier time series to the complex Fourier time series, you will have not only positive frequency, but also have negative frequency. Okay. Let me repeat. From real to complex, you do not have negative frequency. But from complex to complex, the transform, after the Fourier transform, you will have not only positive, but also negative. Okay? So this is one thing. But if we want to do the time transform first, K transform later, or K transform first, time transform later, doesn't matter. That's all the same. But at least in the second step, you need to consider both positive and negative frequencies. Okay, that's the one thing. Right. So now consider two rounds of Fourier transform, once in time, one in space. So that's called FK transform, right? So FK transform, the frequency spectrum now becomes a two-dimensional, not only one single frequency axis, but now have a temporal frequency axis, but also have a spatial frequency axis. Okay, in the two-dimensional domain, two-dimensional space can separate different events, different signal by its dip in the 2D spectrum. The dip is physical meaning will be inverse velocity. We will see it later, okay? So because you know the dip, because you know the inverse of dip, which is velocity, you can easily separate the spectrum, keep what you want, suppress what you don't want, right? Which means filtering. Filtering means whatever you want to keep it, you just multiply by 1. Whatever you want to suppress, you just multiply by 0, right? And then, of course, in between 1 and 0, you do need a tapering. You always need a tapering, otherwise it's straightforward, okay? Let's have a break, and we'll go to detail after the break.